We said that you could think of work as the amount of energy given to an object. So, for example, if I tell you I do 400 joules of work on an object, you know that I have given 400 joules of energy to the object. One thing you are not told, however, is how rapidly I am giving energy to the object. Do I give those 400 joules in 2 seconds total, or do I give that energy more slowly? Maybe I have given 400 joules of energy over a time interval of 10 seconds. In the first example, we give 400 joules of energy to an object in 2 seconds. I am averaging giving 200 joules of energy per second to the object. In the second scenario, where we give 400 joules of energy over an interval of 10 seconds, I am averaging giving 40 joules of energy per second to the object. Power is the rate at which we transfer energy to an object with respect to time. So let's say we're doing work on an object. We are pushing on an object with a force F. That object undergoes its displacement, and therefore we have done some amount of work on the object. Now, the object will not undergo its displacement instantaneously. It does take an interval of time that is greater than 0 to move from point A to point B. So I would say that the rate at which we give energy to the object, the power, is the work done on the object divided by this time interval delta t. Now, if I wanted to, I could write work as FD cosine theta, and I'm going to choose to rearrange the order of the terms in this equation. So I'm not changing the equation in any way. I'm just bringing the force F and cosine theta, where theta is the angle between the direction of the force and the direction of the displacement. I'm just bringing these terms out front. And if I think about d as the displacement of the object, well, I could write d as a delta x. I'm not really changing anything. Displacement is your change in position. And the reason I am explicitly rearranging power and writing it in this form is delta x over delta t looks very similar to velocity that we talked about much earlier in this course. So if I want, I could write power as FV cosine theta. And this is the power at any instant in time. So if I am pushing on an object with a force F, and at some certain instant, that object is moving with a velocity v. Remember, both force and velocity are vector quantities. They will have some orientation. They might be parallel with each other. They might be anti-parallel or something else. These vectors will have some angle between them, something between 0 and 180 degrees. So theta is the angle between the force vector and the velocity vector. And this is two different ways that we could write the equation for power. We could write power as the work done on an object over some time interval, and this is often called the average power, or we could write power as FV cosine theta, and this is often referred to as the instantaneous power. The unit of power in the metric system is the watt, and 1 watt is 1 joule per second. So, for example, a 60-watt light bulb gives off 60 joules of energy every second. And in the imperial system, the unit of power is the Lamma thrust, or sometimes the zebra force. In this example problem, we are told that a train accelerates from 0 to 0.62 meters per second in 21 milliseconds. We're told that the mass of this toy train is 875 grams. The first thing I'm going to do is I'm going to remember that we always want to be working in units of meters, seconds, and kilograms. So that means I'm going to change the mass of the train from 875 grams to 0.875 kilogram. And I'm going to say that 21 milliseconds is 21 thousandths of a second. So I could write the time as 0.021 seconds. Now we have everything in units of kilograms, meters, and seconds. The first part of this question asks us, what is the force with which the motor pushes the train? Well, I know that force is equal to mass times acceleration, And presumably the force of the motor pushing the train will be in the same direction that the train accelerates. So presumably the force of the train's motor will be pushing it along the track. So if I know the mass of the train and I know the acceleration of the train, I could solve for the force of the motor. We are not given the acceleration of the train, but we have enough information to find the acceleration of the train. I could say that v equals v initial plus at. The final speed of the train, we were told, is 0.62 meters per second. We were told the train initially is at rest. And then I could say plus acceleration times time. In this case, the train accelerates in a very short amount of time. And now I could solve for the acceleration, and I find the acceleration of the train is 29.5 meter per second squared. Now that I have the acceleration of the train, we were given the train's mass, I have enough information to find the force with which the motor pushes the train. So I could now say that the force of the motor pushing the train is 0.0875 times 29.5. And when I put these numbers in a calculator, I find the force of the motor pushing the train is going to be 25.8 newtons. In the next part of this problem, we are asked what is the work done on the train by the motor. So, in other words, we are basically asking how much kinetic energy does the train's motor give to the train when the train goes through this interval of time. So to draw that out, we will keep the force of 25.8 newtons. I'll just write it up here. And I'm also going to write down the acceleration. We will use that in a bit in this problem. So the acceleration we found was 29.5 meter per second squared. So the work done on an object could be written as Fd cosine theta. In this equation, F is the strength of the force pushing the object, D is the displacement of the object, in other words, how far it moves, and theta is the angle between the force vector and the displacement vector. Presumably, the force vector will point in the direction that the train is moving, because if we want to make an efficient motor, we're going to have the train move in the same direction that we push it. So the force vector will point along the track, and the train will move along the track. In this case, this implies that the angle between the direction of the force and the direction of the displacement is 0. So we already found the force with which the motor pushes the train. All we need to do is find the displacement of the train when it goes from 0 to 0.62 meters per second, and we'll be good. To find the displacement of the train, we could use a different idea from 1D motion. We could say that v squared equals v initial squared plus 2a delta x. We know the initial and final speed of the train. We found the acceleration of the train. So the only thing left that's unknown is how far the train moved. And this delta x will be the same as the train's displacement during this motion. So I could plug numbers in. I could say v final was 0.62. We'll square that. V initial was 0. I will write it in just to be thorough. Plus 2 times the train's acceleration, 29.5, times delta x. And then I solve this and I find delta x is going to be equal to 0.00651 meters. Now that I know how far the train has moved during this displacement, I know d, I know the force of the motor pushing on the train, and I know the angle between the direction of the force pushing on the train and the train's displacement. So I could write the work done on the train as W is equal to force 25.8 the displacement of the train, how far it moved, 0.00651 times the cosine of the angle between D and F. These vectors are parallel, so the angle will be 0 degrees. And when I put these numbers in a calculator, I find the work done by the motor pushing on the train is 0.168 joules. So in this very short time interval, the motor gives 0.168 joules of energy to the train. Now we could ask, what is the power delivered to the train by the motor? So basically, we are asking how much energy per second is the train receiving energy from the motor. So I could say power is equal to work done over some time interval, and we found the work done as 0.168 joules. The time interval from initial to final is this time interval 0.021 seconds. And from that, I find the average power delivered to the train by the motor is 8 watts, where in this case, the W does not stand for work. The W stands for watt, the SI unit of power. In this final example problem, we are told there are some skiers that are being pulled up a hill by a motor, and the motor has a power of 22 kilowatts. Now, we always want to work in base SI units involving kilograms, meters, and seconds. So instead of writing the power as 22 kilowatts, I want to write the power as 22,000 watts. So this means the motor delivers 22,000 joules of energy every second. To answer this problem, we will need to look at the forces acting on the skiers. We have a downward force of gravity, a normal force that is perpendicular to the slope, and we have the force of the motor that is pulling the skiers up the hill. To look at these forces individually, we're going to set up an XY coordinate system. Because we have a slope, we will want our x-axis to point along the slope and our y-axis to point perpendicular to the slope. So we're going to draw that in. I could say here is the x-axis that lies along the slope, and the y-axis will be perpendicular to the slope as such. When I draw this out, I could say here is the y-axis and here is the x-axis. Here are the skiers on the slope. And I have three forces acting on the skiers. I could say there is the force of the motor pulling the skiers in the positive x direction, force of the motor. I have the normal force that is perpendicular to the slope, F normal. And I have the force of gravity that is pointing in the third quadrant. So the force of gravity is going to look something like this. Now, I know that because the skiers are moving at constant speed, these forces have to sum to 0. We were told constant speed. That basically tells me that because the skiers are moving with a constant velocity, they're not changing their direction and they're not changing their speed, the acceleration of the skiers will be 0. And because the acceleration of the skiers is 0, I could say the net force on the skiers is also going to be 0. Specifically, the force I'm going to be interested in learning about is the force of the motor. Now, the normal force does not have any horizontal component associated with it, so I know that the force with which the motor is pulling the skiers in the positive x direction, that must be the same with which the force of gravity is pulling the skiers in the negative x direction. The force of the motor pulling to the right must be equal and opposite to the force of gravity pulling the skiers to the left. So I'm going to break the force of gravity into its x and its y components. The force of gravity on the skiers is given by F equals mg. So I could write the force of gravity on the skiers to be written as the total mass of all the skiers. The total mass of all the skiers is 18 times 52 because we have 18 skiers of mass 52 kilograms each. And the acceleration due to the Earth's gravity is 9.8. So if I put this in a calculator, I find the force of gravity is 9170 newtons. Now, this 9170 number is the magnitude of the gravitational force, but we want to break the gravitational force into its horizontal and vertical components, because we know that the horizontal component of the force of gravity will be the same size as the force from the motor, because these two forces do need to cancel. So to find the horizontal component of the gravitational force, I need to be creative with some trigonometry. So let us look at this picture. I could draw a line straight down from this gravitational force vector that I drew on the image. And if I notice I have a 14-degree angle right here and a 90-degree angle right here, this indicates that this angle will be 90 minus 14. So this angle is going to be 76 degrees. That tells me that this angle right here is 76 degrees, and this angle from the positive x-axis to the force of gravity vector is going to be 180 plus 76 degrees. So this angle right here will be 256 degrees. 180 degrees from the positive x-axis to the negative x-axis, and then we add 76 more degrees as we sweep down into the third quadrant. This means that I could write the horizontal component of the gravitational force, F grav x, as 9170 cosine of 256 degrees. If I put this number into a calculator, I get the gravitational force in the x direction is negative 2220 newtons. Because the skiers are ascending the slope at constant speed, I know the backwards force of gravity is going to be the same as the forward force of the motor. So that means the force of the motor must be positive 2220 newtons. Now that I know the force of the motor, I could write the force of the motor is equal to 2220 newtons. We can begin to solve for the speed at which the skiers are ascending the slope. We are given information about the power of the motor. We now know the force with which the skiers are being pulled. We have two options for solving the speed at which the skiers are moving. We could say power equals work done over some time interval, or we could say power is equal to FV cosine theta. Looking at these two equations we have for power, the first equation I wrote describes the average power delivered to the skiers by the motor. This equation is not going to be very helpful to us. The reason for that is if I write work as FD cosine theta, in this equation, D is the displacement on which the skiers undergo, basically how far the skiers travel. We do not have that information. Also, delta T over here is the time interval. How long are the skiers pulled for? That is also a piece of information we don't have. However, if I look at this other equation, we know the force with which the skiers are being pulled by the motor, we know the power of the motor, and we know the angle between the direction of the force of the motor and the direction with which the skiers are moving. So in this second equation, we have everything we need except velocity, which is what we're trying to find anyway. So I am going to use the second equation to write power as 22,000 watts is equal to the force of the motor, 2220, times the speed at which the skiers are moving, times the cosine of the angle between the force vector and the velocity vector. The force vector points up the slope, the velocity vector points up the slope. These two vectors are parallel with each other, so I would write that as theta equals 0. So I have cosine of 0. Now, when I plug these numbers into a calculator, I find that the speed with which the skiers ascend the slope becomes 22,000 equals 2220 times v. Cosine of 0 becomes 1. And I find that the speed with which the skiers ascend the slope is 9.9 meters per second.